Okay, part 185 is line 18a4c. This is argon gas, Boyles law, kinetic energy, Wow Seti. There's the alien radio signal. Here's a picture of argon gas bubbles. And it says determination of viral coefficients for argon gas at 323K. And it's from Tandy Grubbs. The goal is to pressure volume data is presented for argon gas at 323.15K. The compression factor Z is calculated for each PV data pair, and a viral equation of state is subsequently fitted to the data, yielding the viral coefficients. The prerequisites: a knowledge of viral equations of state for describing non-ideal gases. Resources you'll need, it's about an exercise background, the pressure, volume, and temperature. And there's the calculation they're going to use. Okay, so Z is exactly equal to 1 for an ideal gas at all pressures. Deviations away from Z equals 1 arise from intermolecular interactions. A plot of Z versus pressure for an arbitrary gas is shown in figure 1. 3 regimes can be identified in this graph. The value of Z tends towards 1 as pressure approaches 0, where all gases tend towards ideal behavior. The value of Z is less than 1 at intermediate pressures because forces of attraction cause the pressure or volume in the numerator of equation to be less than their ideal value, and the value of Z is greater than 1 and ultimately tends towards infinity at high pressures because repulsive forces cause the pressure or volume to be greater than their ideal values. And this is www.stetson.edu, and here's a graph. The data was obtained from Blanchett L. and Hall, KR FCF 4775-91, 1970. The first column of numbers is the pressure of argon gas in units of atmospheres, and the second column of numbers is the corresponding molar volume of the gas in units of liters dash mole. Okay. The temperature of the gas was held constant throughout the data collection at 323.15 Kelvin. So the PV data for argon, and there's the link to it. The next word that comes up is Boyles law, and that's from the Stetson Edu website. You are encouraged to submit your own data-driven exercise to this web archive. All inquiries should be directed to the curator, Tandy Grubbs, Department of Chemistry, Stetson University. I'm not sure if they're still there. This is from 1970, so there's the email there. Okay. So here's another diagram here. This is an animation showing the relationship between pressure and volume when amount and temperature are held constant. And the quotes from Wiki are Boyle's law, sometimes referred to as the Boyle-Mariotti law, is one of many gas laws, and a special case of the ideal gas law. Boyle's law describes the inversely proportional relationship between the absolute pressure and volume of a gas, if the temperature is kept constant within a closed system. The law was named after chemist and physicist Robert Boyle, who published the original law in 1662. The law itself can be stated as follows. For a fixed amount of an ideal gas kept at a fixed temperature, P pressure and V volume are inversely proportional, while one doubles the other halves. There's a diagram. That's a graph of Boyle's original data. Okay. In 1687, in the Philosophiae Naturalis Perspicia Mathematica, Newton showed mathematically that if an elastic fluid consisting of particles at rest, between which are repulsive forces inversely proportional to their distance, the density would be directly proportional to the pressure. But this mathematical treatise is not the physical explanation for the observed relationship. Instead of a static theory, a kinetic theory is needed, which was provided 2 centuries later by Maxwell and Boltzmann. The kinetic theory of gases describes a gas as a larger number of small particles, atoms, or molecules, all of which are in constant random motion. The rapidly moving particles constantly collide with each other and with the walls of the container. Kinetic theory explains macroscopic properties of gases such as pressure, temperature, or volume by considering their molecular composition and motion. Essentially, the theory posits that pressure is due not to static repulsion between molecules, as was Isaac Newton's conjecture, but due to collisions between molecules moving at different velocities through Brownian motion. While the particles making up a gas are too small to be visible, the jittering motion of pollen grains or dust particles, which can be seen under a microscope, known as Brownian motion, results directly from collisions between the particles and gas molecules. As pointed out by Albert Einstein in 1905, this experimental evidence for kinetic theory is generally seen as having confirmed the existence of atoms and molecules. Now here's another graph for you. It's called the temperature of an ideal monomatic gas is a measure of the average kinetic energy of its atoms. The size of helium atoms relative to their spacing is shown to scale under 1950 atmospheres of pressure. The atoms have a certain average speed, slowed down here to 2 trillion-fold from room temperature. So there's the speed of molecules. That's the equation. And it's in kelvins. R is the gas constant. The molar mass is given as kg mole. The most probable speed is 81.6% of the RMS speed, and the speed means 92.1% distribution of speeds. The next keyword that comes up is a neutronic fusion, and I googled it in the next module, so we'll go on to the next one now.